Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, I'll be talking with Thor Matteson, a structural engineer and the head of Quake Brace manufacturing company based in Emeryville, California. Thor is also the author of two highly regarded books, Wood-Framed Shear Wall Construction, an Illustrated Guide, and Earthquake Strengthening for Vulnerable Homes. And this episode, we're actually going to be talking about a new bracing system called SkinnyBrace that can help you in your seismic retrofitting projects, especially for soft stories. I'm your host, Matt Picardal, and this is the Structural Engineering Channel podcast. Now, let's jump into our conversation of the week with Thor. Thor, welcome to the show. Can you start by introducing yourself and tell us a little bit about what you do on a daily basis?
Sure, thank you. I'm a structural engineer in Emeryville, California, so that's in the San Francisco Bay Area. I've got about 15 years of experience doing soft story designs, retrofitting buildings in the San Francisco area particularly. I got frustrated waiting for a product that would do everything that we needed it to, which is fitting into very small spaces available in the existing buildings. So I ended up inventing my own system, and I now manufacture that, and I'm trying to spread the word on it, or spread the word about it to other structural engineers and building owners so that they can use it in their soft story retrofits.
Yeah, thanks. And I am really curious about, you essentially just made a whole new bracing system from scratch, it looks like. Could you go into the story? Because I imagine that takes a lot of work and analysis and getting it approved. What was the story behind that? How did you go about doing that, and how you came up with it and the whole process of getting through it?
Okay, so the whole challenge of putting a soft story retrofit system into an existing building is not always the bracing system itself. It's just finding room in the building to accommodate new elements. And in San Francisco especially, you've got basically one prototype building, and it's got a garage and an entry step, entry stairs or an entry downstairs, and then a service entrance. And you can mix those up, but they're always there at the front of every building. And the typical building width in San Francisco is 25 feet. So between a garage door and entry steps and the service entrance, you really don't have much room to put in a steel frame or a shear wall. So what we ended up doing was using special cantilevered columns, which have a dismal R factor of 2.5. So that means you just have enormous seismic forces. You need to have a very big footing for resisting the overturning. The diaphragm might need to be reinforced, and it's just a really onerous situation. The other option is to put in a conventional moment resisting frame. That often means you need to relocate an electrical panel, or if it's an apartment building, you need to relocate multiple electrical panels. And the same on the other side of the garage, there are going to be gas meters that you need to move. So that can, just those utilities can cost more to relocate than the actual frame installation. So I wanted to come up with something that had a better R factor so that we weren't getting killed on the seismic forces, and something that would be easier to repair, something that would fit into the narrow spaces. And so that was the inspiration for the design, was getting something that would mount on top of a narrow steel column, but would have the ductility needed to give you that higher R factor. So that was the inspiration for it. And the testing and the development followed that over a few years, and doing some tests at sort of a hobby garage that the city of San Francisco had set up, and that was the proof of concept. And then we did actual testing at UC Berkeley's laboratory.
Yeah, really interesting. So it looked like there was a lot of pain points with getting the existing code, structural systems like the moment frames and whatnot. And like you were saying, just even moving the existing utilities sometimes would cost more just because there wasn't enough room with what we had in the code book. So you made your own.
Right? Yeah, more or less. And we actually tested it using test protocols that are applied to wood frame shear wall substitutes. So if you think of the sort of proprietary shear wall systems that mount on either steel studs and have OSB and a bunch of strapping and stuff, that same testing procedure and criteria is what we applied to this, even though it's a steel column. So it kind of confuses people sometimes on, well, why did you use the test criteria for plywood shear walls? And that was because the rest of the bracing system in a typical soft story retrofit will be the wood structural panel shear walls. So we wanted something that was compatible with those, and basically it could substitute our products in place of a wood structural panel shear wall.
Gotcha. And yeah, for our listeners that may not be too familiar with maybe the seismic codes here in California, or the students, you'll in San Francisco, there's usually, like you were saying, two stories. The first story is usually a garage, and in the garage there's big openings for those cars, so that causes a like you were saying, a soft story. And what the engineers often do here in California is, I think the default method is they install some big moment frame or some big frame. It's very costly for the owners because there's no room. You got your car there, and then now you got this big moment frame. So could you show us and explain more on the SkinnyBrace system that you came up with, and how that makes it different from what we typically do?
Sure. I've got a model here that is not actual steel. So when you get one, this is not going to be flexible by hand. But this would be a standard wide flange column that this mounts on. The blue here is the structural fuse assembly. And this taper here is a parabola. So basically you've got a linear increase in the section modulus from between these two bolts. So what that means is you can sort of control the point at which this yields. And so what we've done is actually tried a few different configurations of this. One was so that the steel started to yield simultaneously along the full length. And as experimenters do, we discovered friction. So that meant that it's really better to have the yielding start at the bottom end and progress upwards as the force increases. So the way that this is connected, if this is the floor framing up above the garage, the column is anchored into a new foundation. And when the seismic force starts applying itself on the floor framing, you start getting this curvature in the structural fuse. So this whole length of steel is absorbing the earthquake energy, and you get a tremendous volume of steel relative to what you might get in some other structural systems, and all this is absorbing the seismic energy. So it's got phenomenal ductility and can go through many more cycles than any other system before it fails. So
yeah, that's really
in
cool.
fact, the FEMA requirements and the steel requirements for pre-qualified moment frame joint is that it has to withstand 2 cycles of displacement at 0.04 radians. So basically that's 4% drift for 2 cycles. we tested ours and got 40 cycles beyond 4% drift, up to as much as 10% drift before it failed. So the
Oh, wow.
steel's just amazing stuff. So after seeing that, when I was doing the experiments, before I was doing the experiments, I was kind of worried about putting these in people's houses, and is it really going to work? And I saw the test results, and it's like, okay, I got no worries now. This is this is
It
not going to
works.
fail. The house or the apartment building will collapse into a heap of rubble before that structural fuse fails. So I'm fully confident.
Very cool. Yeah. So for our listeners that can't see the demonstration, there is something on the website that will link below. But if you're watching this on YouTube, you should have saw that. And if I can just explain it, to me, it looked like you got a steel column, and at the top you had essentially a reduced beam section or a piece of steel that's meant to rotate and deform under earthquake loads. And it's separate from the steel column. So when the earthquake hits, that piece of deformed metal will absorb all of the earthquake energy. And I think theoretically you could replace it if it gets mangled during an earthquake, right? It looked like it
Correct.
was
Yeah,
kind of replaceable.
we'll find out. There could be other things that deform in the system, but the idea is that those two plates, and the video or the demonstration, you only see one, but there are two of them. So the column that they mount to is sandwiched between the two structural fuses, and you could remove 3 bolts, put new structural fuses on, and be ready for the next earthquake. And if you compare that to most other systems, it's going to be much easier to replace those parts than replacing, say, a buckling restrained brace, or the replaceable parts in one of our competitors' frames. You have to remove 40 to 48 bolts before you can replace those parts, and they're a lot harder to get at. So we're hoping that this would be much easier to get up and running after an earthquake.
Yeah, so it's essentially a cantilever column. So you install one column, but it's also ductile with the ductility of, say, some of those like BRB braces, really ductile systems, RBS moment frames. So it's a cantilever column, but it's ductile. So I think that's a pretty cool concept. And could you go through some of the comparisons on maybe some of the, like you were suggesting, like what do you have to do for a moment frame or a brace frame versus this, in terms of maybe the installation or the components that I guess when you're doing a retrofit, what are the pros and cons versus traditional methods and this? Because to me it looks like, oh, you just install one column, but I'm sure there's more. But yeah, can you get into that a little bit more?
That's you're actually pretty close. The moment frames in San Francisco or most other existing buildings, you might need to make the garage door smaller. I joke with people, it's like, well, you might just need to buy a new car to accommodate your retrofitted building. And the utilities problem is huge. There are a lot of 3 to 6 unit apartment buildings in San Francisco, and they've got 3 to 6 electric meters and 3 to 6 gas meters, and the pipes from those snake all over the place. So finding one plane near the front of the building where you can have a column on one side, a column on the other, and a beam going across, you're almost always going to hit a lot of stuff with those 3 items. If you have the SkinnyBrace system, so named because it will fit into very skinny spaces, you just need to find one place that you can go up from the footing to the second floor framing and make a connection at that point, and you've missed all those utilities. So it's much easier to find a place to install a SkinnyBrace, or a cantilevered column. I hate to mix the term cantilever column when I'm talking about the SkinnyBrace, because it just sets off alarm bells in people's minds if they're accustomed to thinking of the R factors for both systems. So, but it's kind of a unicorn. It doesn't really have a place to go in the code, unfortunately.
Yeah, it's almost a brand new system in terms of the way it's designed. That's pretty cool in terms of now you only just need to install one column, and that's it.
Yeah, and I try to, I mean, like I said, we do test it according to wood structural panel shear wall protocols. And so if you want to think of it as being, for example, one of our models has the same strength as 13 feet of plywood shear wall with 2-inch edge nailing, and that fits in a 13-inch wide column. So, you're collapsing maybe 20 feet of wood structural panel into a very nice narrow system.
Yeah, and I think the cool part is that you built in that resiliency with the system. It's very resilient, and it can be theoretically repaired or replaced. So it's not just like a one and done system. Hopefully it can, like you were saying, can last multiple earthquakes.
Right. And right now, at least ANSI is starting to look at sustainability of building systems, and we might be working toward getting something like that included into the building code. But right now, we've just got a bunch of basically disposable buildings. When the earthquake comes and your moment frame yields and goes into plastic bending, you've got a 3,000-pound piece of trash that you need to jackhammer out of the foundation and haul off and replace. So that's a lot of work, a lot of energy, a lot of time. If you have an entire area that's been hit with earthquakes, you're going to have every contractor west of the Mississippi showing up with their crew and trying to figure out how to do stuff and tripping over each other, and it's going to be a nightmare in the Bay Area after that.
Yeah, I can imagine. And I know you've had some experience with the contractors and I believe construction yourself. What things that did you look out for when you were creating this in terms of, okay, it's skinny and it's resilient and it's really great, but in terms of the constructability of it, what things did you design or take into consideration for easy installation for the contractors?
Besides just the overall fact that it can fit where practically nothing else can, I also included the brackets that connect between the top of the SkinnyBrace and the wood framing. I incorporated loops that you can hook hoists onto that will, so you can hoist the steel column up into place. And with one of the models or one of the connection options, those loops are placed on the center line of the column. So you hoist it up and it's almost perfectly aligned, and the bolts from the bracket slip down into the top of the SkinnyBrace as you're hoisting it. And it's really easy. I can install one myself in about 20 minutes. So that, so easy, even an engineer can do it.
That's a good way to put it. Yeah, so it seems like even like you were saying, I saw the video of it. So if you guys haven't checked out the website, check out the website that's linked. And yeah, there's a lot of pictures and a lot of demonstrations on there. Really cool to see. And I think I even saw a picture of you installing it with that hoist. Like it's almost, is it a one-man job essentially where you can just hoist it yourself and just pulley it? Maybe not recommended as a one-man job.
Right. Yeah, it could be. And the smaller model that works for a single car garage or with a single floor above it, that model weighs about 300 or 400 pounds. It's mounted on a W8 by 35, so the fuses add 50 pounds or so. The bigger ones, they're mounted on a W12 by 136, so that starts to weigh, possibly 3/4 of a ton. So that we hope you're going to have a crew to install.
Yeah.
If you were adventuresome, you could, one person could do it. I mean, I think there are probably very few contractors that would not have a crew of at least 2 people working on this. But
Yeah.
it doesn't take a forklift. It doesn't take, a crane, which is going to be impossible to get into an existing building anyway. It doesn't take a bunch of cribbing to support it, so it really can get hoisted up pretty well. And the other benefit of that is the steel brackets are meant to resist, 10,000 pounds of earthquake force. So they're connected quite well to the structural framing of the building. And if you're hoisting from that support system, you can be pretty sure that those connections are good. And if you have no idea of how contractors hoist things into place, you might be terrified going out into the site and seeing how it's done in the field sometimes. I mean, they'll just drill a hole through a joist and put a chain through it and hook their hoist onto that, and it's not done by engineers. We'll put it that way.
Yeah. Yeah. And I know I've talked to some other engineers that have made new products. I know it's challenging. Could you explain the for example, like the code evaluation report in the structural engineering field? I know it's important for us as engineers to have that. And how did you even get that? I imagine there's a lot of testing going into it and getting it approved by all the codes and safety.
Sure. The code evaluation report is the approach that's used to meet the IBC or California Building Code provisions for alternate methods of construction and design and materials. And so a code evaluation report comes from an accredited evaluation agency. There are probably about 20 of those. The ones that everybody has heard of are the ICC Evaluation Service and IAPMO Evaluation Service. There are other ones. DRJ certifications is the ones that we used. They had an approach that was we felt was going to be more expedient to get several models of the SkinnyBraces evaluated. And all of those are accredited by the American National Standards Institute accreditation board. So, a building inspector or a plan check engineer or a design engineer can look at the report, and if it's done by an accredited evaluation agency, that's their assurance that the test results and the analysis and the quality control, all that's in place to assure that you've got something that's going to work the way the manufacturer says it is. So that people who ask me about the invention, sometimes they're really impressed that I got a patent on it. Well, that just takes $30,000 that you kind of throw at a patent attorney. But getting the evaluation report was a lot more painstaking and required a lot more analysis and paperwork and quality control systems being set up and that sort of thing.
Was it I know you mentioned you said the patent parts. Okay, that's probably the easier part, but I feel the code, was it the ICC report or the EAMPO code reports or approval? I feel those people say those are strict. Was that the hardest part in terms of getting approval? You got to provide all of these testing criteria and follow whatever they want. How did that go?
So the biggest part of that was the quality control aspect, where we do need to track all the parts and the steel that's used, and the the heat numbers for the steel used in the structural fuses. So if there's some problem, we can go find those out in the field. So we track everything down to the nuts and bolts that we use to connect everything together, and the steel and all that, so that we can trace any problems that might arise. So that was the most difficult, because there's not really a template for a 30-page quality control manual in Word that you can bring up and fill in the blanks. So we kind of came up with that from scratch. And then doing all the testing had to be done to the proper protocols, and it had to be done at accredited laboratories and stuff. So it's all, and all those processes and criteria and rules are in place. They're just not easy to find, and finding a testing lab that could actually had the output forces that we needed to test these was pretty difficult. There was a private laboratory that we used, and we almost broke their equipment. I mean, they actually set up the test in a manner that I didn't feel confident in, and I pointed it out to them, and they said, "Oh no, it's fine. We do this every day." And we're in the middle of a test, and something went snap, and that was the end of the test. So we had to, after that, we went to the UC Berkeley lab, where they had some giant actuators that would put out 200 kips. So that was enough for us at this stage.
Yeah, next test, that one was to meet the requirements. Yeah. And I know, so since this is a new system, I think I imagine structural engineers that look into this and want to use it for their retrofits, they may have some challenges, maybe or maybe not, but I imagine they would have some challenges convincing the owner to use this new product for their building, when maybe it's newer and maybe the owners might not be completely comfortable with it. So I guess, what are some of the ways that we could get this product more, I guess, accepted in the construction industry?
So actually, it's kind of the other way around. The contractors and the owners are usually very enthusiastic about it. They look at something that's faster to install, costs them less, doesn't take up as much space in their carport or their garage, and they're usually all for it. It's some engineers can be more hesitant to use something that hasn't been tested by earthquakes. It's only been tested in a lab. And that's if you're extremely conservative, that's a legitimate concern. And the other pushback that we get from is from building departments. In particular, there's one city and county that I won't name that won't accept our evaluation report. They only accept evaluation reports from 2 of the agencies that I named, which is kind of like saying you need to hire an engineer to do your design, but their name needs to begin with A through G. So they accept evaluation reports from ICCES and IATMO UES, which have no better accreditation credentials than our evaluation agency does. But that's the big challenge. And engineers, once a lot of them say they see the test videos, they're fairly, they're impressed well enough, and then knowing that the evaluation report is there, they're pretty happy with it. So that's the big challenge is building departments that kind of want to reinvent the wheel and do more analysis or more a peer review of the evaluation report, which is itself already a peer review.
Yeah. Yeah. So it seems like a lot of the pushback would probably be from the cities in terms of owners, contractors. They like it because it's, like you were saying, easier to install, cheaper, and uh, they can they need less room. And the engineers' point of view, I think for most engineers, that, like you were saying, once you have those ICC reports and multiple testing reports, and they see the how it works on the videos also, and getting all the testing and seeing the testing too, I think for most engineers, they'd probably be comfortable with it. But I guess those big cities, or maybe not big cities, but some jurisdictions might have issues with it. And who, who knows how you can try to convince them. I think you could try to uh, do all that you can to convince them, but sometimes the cities just won't budge, or they just don't. But it looks like that's not the majority. It looks like most of the jurisdictions, you prevent them with this case and you got the engineer on board. Shouldn't be a problem.
And the cities, if you go to the right spot on the ICC website, they actually have it's under the members only page, but they have a procedure, a little checklist that you can go down just to see if an alternative construction material is acceptable. And just using the checklist on their website, I made a little PDF presentation that shows exactly how our evaluation report meets all their requirements. So it's in my opinion, I'm kind of surprised that a plan checker would want to do that, because I guess there might be questions that you have. Is the report actually up to date? And that is reasonable and easy enough to check on the evaluation report, but there are a whole bunch of other things that you can check. And so the ICC has already got that list of things for building officials to tick off if they feel the need, and we meet all the criteria for that.
Do you have any final piece of advice for maybe aspiring entrepreneurs or engineers who are maybe looking to come up with their own innovative solutions like you did?
I guess the biggest one would be really patient with the process, because it takes far longer than you think it should. And you might also get opposition from people that you originally think ought to be embracing the product. I was really pretty disappointed to have invented this to address buildings in San Francisco, and the seismic safety program people there were really enthusiastic about it. And then the building department just said, no, we need to see a peer review for every installation of this, unless it's in a single family home. And I took the demonstration model that I showed you earlier to a structural engineers convention one time and was showing it to people, and I basically got two responses. There were engineers who come up and say, wow, I can't wait to use that in my designs. It looks really efficient and really great. And what a great idea. And the other response was, wow, that looks like a great idea. Good luck ever getting it approved. So I don't know what level of knowledge that second group had, but it was kind of foretelling of the experience that I was going to run into. So,
Yeah.
and the other advice, and I hate to give it because the evaluation agencies that are accredited, they're really all equally qualified. But if you want to get something that everybody's going to recognize, go with the major evaluation agencies because everybody's heard of them and the name is going to be recognized everywhere, which is just, I hate to say that because it sort of squeezes out the other ones that are perfectly qualified and just have a different approach in their methods of evaluation.
Yeah, thanks for the practical advice. I know, like you were saying, it's when you're coming up with something new, I think especially with new structural systems, it's going to be tough, but I mean, you did it. So congratulations on that. And thanks again for joining us, Thor.
All right. Well, thanks for having me, and look forward to spreading the word further and selling more of these and protecting more people. So I appreciate what you're doing.
Absolutely. Thanks. Hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, as well as links to any of the resources or websites mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. And until next time, we wish you the best in all of your structural engineering endeavors.